Hello chemistry fans, and welcome back to chemistry problem solving session for Chemistry 1032 here at the Academic Success Center. I am Dr. Russell Betts and I am your host for today's question. So let's take a look at it. Chapter 6, problem 8. If the following pairs of atoms made bonds, would the bond be polar covalent, nonpolar covalent, or ionic? Alright, well, this is a very interesting question. Not a very difficult question, I have to tell you. But it has some words we're probably going to want to look up. So let's discuss. Nonpolar covalent. Well, that means the bond is not polarized, which means the electrons in the bond are not being pulled to one atom or the other in the bond. That's what nonpolar basically means. The two atoms are typically nonmetals and they're sharing electrons somehow. And no atom in the covalent bond has the electrons more to their side than the other atom will. If you want to think of it this way, the atoms are equally using the electrons, which leads us to polar covalent. Well, polar covalent is like one atom in the covalent bond is pulling the electrons towards itself more efficiently, let's say, than the other element or atom in the bond. Think of a tug of war where there's a flag in the center of the rope. One team of tuggers is pulling the rope, the other team is pulling it in the opposite direction. When one team is stronger than the other, the flag will move towards the team that's stronger, or the team that's pulling the flag closer to them. Think of the flag as the electrons, pulling the electrons closer to the stronger team in the tug of war. I hope that's a pretty good analogy for you guys. Now, an ionic bond is basically when one atom flat out takes the electron from another. For example, when a metal and a nonmetal bond together, the metal will typically get the electron stolen from it, and the nonmetal will typically steal the electron. That's generally how it works. So, in order to discuss polar covalent, nonpolar covalent, and ionic bonding, you have to discuss electronegativity. Now, electronegativity is the amount of attraction, let's say, an atom has for the bond electrons. Okay? Atoms like fluorine have an extremely high electronegativity. It's valued at 4.0. It's the highest one on the periodic table. Nonmetals in general have fairly high electronegativities. Metals in general have low ones. So in general, and this is pretty much true, nonmetals want to take electrons or can pull electrons to themselves. Metals want to get electrons taken from them, and for reasons we've discussed in other videos. So now, if we want to talk about nonpolar covalent, we have to look at the difference in electronegativity. So for example, we have two elements that are bonding together, two atoms that are bonding together. We take the electronegativity of one and the electronegativity of the other and simply subtract them. And if the difference is 0.0 to 0.4, so basically 0.4 or below is the difference in electronegativity, that bond is considered to be nonpolar covalent. The electrons are not being pulled to one end of the bond or the other. It's kind of in this, like being shared equally by both. So that bond is considered to be nonpolar covalent. Now, polar covalent has an electronegativity difference. Now, we're always talking about the differences here. Greater than 0.4 and less than 1.8. So it's 0.4, it's greater than 0.4 and less than 1.8. So 0.5 to 1.7 difference is considered polar covalent, where the bond electrons are being pulled to one end of the bond or the other, depending on who's more electronegative. And then it brings us to ionic. If you are greater than 1.8, you're ionic. So if the difference between electronegativities is greater than 1.8, the covalent bond is not even forming. It's just a flat-out theft of an electron by a nonmetal, typically to a metal. And that's an ionic bond. Now, to figure this out, you have to have what's known as a electronegativity chart. Just a chart of electronegativities. And luckily for us, in our textbook we're currently using, there's a chart of electronegativities right there on page 189. Now, I'm sure these videos will outlast the book, so other books will have the table on a different page, but every general chemistry or 1032 chemistry textbook will have this table. So I'm getting the numbers that I'm going to be throwing around here in a moment all come from this table. All right, so now let's do this problem. We're going to make a bond between sulfur and oxygen. They're both nonmetals, so we expect it to be covalent. But is it polar covalent or non-polar covalent? That's the question. So we have sulfur bonding to oxygen. The electronegativity of sulfur from the chart is 2.5, oxygen is 3.5, for a difference of 1.0. The electronegativity difference is 1.0. That makes this bond polar covalent. Now, the question doesn't ask me to do this, but I'm going to do it anyway. I'm going to assign what's known as delta negative and delta positive, or who's drawing the electrons closer to themselves. So let me just write it down, I'll explain it. This is delta negative, that's delta positive. Now, delta negative means the oxygen is forming a slight negative charge. The sulfur is forming a slight positive charge, and that's because the oxygen is pulling the electrons this way, away from the sulfur, causing the oxygen to become partially negative, not 100% negative, not ionic, just slightly, okay? And we're not going to give that delta any magnitude. We're not going to say it's like 0.6 of a negative. We're just going to say it's slightly negative, okay? But that makes this bond polar covalent. All right, next. Barium and sulfur. All right, well, barium is a metal, and sulfur, again, is a nonmetal. So we expect this bond to be ionic. So let's write the numbers down. 0.9, and sulfur is 2.5. So let's do the math real quick. I don't want to use my head today. I'm just going to use a calculator. 1.6 is the difference. Now, according to the convention, this bond will be polar covalent. So that's good, polar covalent. Next, silicon and nitrogen. Silicon's electronegativity is 1.8, nitrogen's is 3.0, for a difference of 1.2. So that bond is also polar covalent. All right, so now oxygen and fluorine, so O to F. Oxygen is 3.5, fluorine is 4.0, for a difference of 0.5. So that makes this bond polar covalent. Okay, so now looking at the next one, the last one, carbon and hydrogen. Carbon is 2.5, hydrogen is 2.1, for a difference of 0.4, and that puts us in the nonpolar covalent realm. So the carbon-hydrogen bond would be nonpolar covalent. And that's how you'd figure it out. Well, before we go, let's assign delta negative and delta positive. For this one, it's nonpolar, so carbon nor hydrogen are delta negative or positive. They're neutral. Here, we have 0.5 difference, so we have to give the fluorine a delta negative, the oxygen is a delta positive. Notice, the delta negative always goes on the atom with a higher electronegativity because it's pulling electrons towards itself. Nitrogen will be delta negative, silicon will be delta positive, barium is delta positive, silicon is delta negative, and we've already done the top one. All right, so I hope that's kind of cleared it up, how to determine if a bond is polar or non-polar. Now this is just for bonds. Molecules could be different, which we've talked about in a subsequent video. So if you have any trouble with this, please go ahead and talk to one of the tutors here at the Academic Success Center, or come on by office hours and talk to me about it during a normal office hour time. Don't sit back on this. It's a pretty important topic. It helps explain a lot of things that are upcoming in this class. And with that, I'd like to say thank you for watching, and good luck and good chemistry.